Hello everyone, welcome to another pre-calculus video lesson. This is a lesson on section 3.1, exponential and logistic functions. Now before we really get into this section, we have to review some basic rules of exponents. So a lot of books call these the laws of exponents. Okay. The first ones are pretty familiar. The first one is a to the m plus n equals a to the m times a to the n. Number 2, a to the mn equals to a to the m raised to the n power. The third one, we have a to the negative n equals 1 over a to the n. Or you can think of this as 1 over a all to the n power. So let's do an example for this particular law. So example, 3 to the negative 4 power is equal to 1 over 3 to the positive 4 power, which is 1 over 81. Okay? The fourth rule, the fourth law says a to the m divided by n power can be written in two different ways. The first way is to write it as a to the m and then the nth root of that. So the nth root of a to the m power. Or you can think of this as the nth root of a all raised to the m power. So both of those work. Let's do a couple examples for that. Well, let's do 8 to the 2/3 power. Well, this can be written as 8 to the 1/3 power and then the to all squared, which is the same as the cube root of 8 all to the second power. And we know that the cube root of 8 is 2, so it's 2 to the second power, which is 4. Okay? Now, let me give you... Oh, what's this? Hold on. Let me get rid of that. Get rid of that. Okay. So we have this right here. Let me shrink... let me shrink that a little. Shrink that a little. Okay. So try this one in your notes. 32 to the negative 3/5 power. Simplify that. Go ahead and pause this video to try to simplify that. Okay, here's the solution. We can think of this as the fifth root of 32 all raised to the negative third power. And we all know that the fifth root of 32 is 2. So we have 2 to the negative third power. And using rule number 3 above, that is just 1 over 2 to the third, which is 1/8. Okay. Okay, let's start talking about exponential functions. The definition of exponential functions goes like this. Exponential functions are functions of the form f of x equals a times b to the x power, where a is non-zero and b is positive. We want to make sure that b is not equal to 1, because then we would have 1 to the x power, which is not very interesting at all. Let's have some vocabulary words down. This a right here is known as the initial value. The b is called the base, and the x, sometimes it's also called the multiplier, or the growth / decay factor. More on that later. The x up here is called the exponent. So let's do an example. Example 1 here says graph f of x equals 2 times 3 to the x power. So a good way to get started on this is to make a table. And I'm going to make the table go from negative 3 to 3. Now it's a good place to start here when x is 0, because that is the initial value. So this is 2. The base tells you what number to multiply by to get to the next output. So the next output will be 2 times 3, which gives you 6. Then you multiply by 3 again, which gives you 18. And you multiply by 3 again, which gives you 54. Now to go in reverse, you would divide by 3. So this would be 2/3. When x is negative 2, y will be 2/9. And then when x is negative 3, y will be 2/27. So, as you can see, we have preserved this pattern of multiplying by 3 if we were to go down the table. Okay, so now we're going to plot these points. It's good to plot the initial value first. So there is 0, 2. Then we're going to have 1, 6, which is right there. Then we have 2, 18, which is all the way up here. If we go the other way, you'll notice that we have outputs of 2/3, 2/9, 2/27. Those outputs are going to get closer and closer to 0. So here's your graph. Notice that it has the shape of an exponential function that you know of from Algebra 2 and also from our basic functions. Now let's look at another example. This time we have to come up with the exponential function formula given a set of values. So here we seem to have numbers that are increasing by a factor of 2. Notice that you have to multiply by 2 to get to the next output. So that tells you that the base is 2. Now, the initial value, you always look at when x is 0. So we are talking about right over here. When x is 0, y is 4. So the initial value is 4. Keep in mind that the initial value is about when x is 0. And so here we have enough to make our exponential function. Initial value times the base to the x power. So this is our solution. Not solution, but this is our function given this set of values. Here's another example. Here, it's not as clear what number we multiply by to get to the next output. But here it seems to be, there's enough clues for us to see that, oh, the answer is 4. So that means that the base is 4. To look for the initial value, we look for when x is 0. So that means the initial value here is 6. So that means our function is f of x equals 6 times 4 to the x. Pretty easy, right? Let's look at this next one. To go from one number to the next, looks like these numbers are getting smaller, which tells us that the base, or the multiplier, is less than 1. And upon closer inspection, we see that the multiplier, the number that we are multiplying to get from one number to the next, is 1/4. So that tells you that the base is 1/4. What about the initial value? Well, once again, we look at when x is 0, and we see that the initial value is 8, which tells us that f of x equals 8 times 1/4 to the x power. Now this next example doesn't have a table of values, but it gives you a graph. And so what I'm going to do is I'm going to try to translate this into a table to help me find the equation of this exponential function. Well, when x is 0, y is 4. When x is 1, y is an unknown at this time. When x is 2, y is 9. So here, we don't know the multiplier right away, so I'm going to call it r for now. So 4 times r equals this number that I have written as a blank, and this times r gives you 9. So what's happening is that I have 4 times r gives you 9. And I'm going to solve for r here to figure out the ratio. So right here we have 4r squared equals 9, r squared equals 9/4, and so r is 3/2. So that's our base. The base is 3/2. And then the initial value, once again we look at the line in the table where x is 0. So that's our initial value, so that's 4. So that's it. Our function is f of x equals 4 times 3/2 to the x power. Finally, we want to answer the question, exponential growth or decay? So let's look at what would make an exponential function an example of exponential growth and what would make it an example of exponential decay. For f of x equals a times b to the x, f of x is an exponential growth if b is greater than 1 and decay if b is between 0 and 1. This makes a lot of sense because if your multiplier, the number that you're multiplying to get from one term to the next, if that number is greater than 1, then the terms of your function are increasing, which means growth. If the base is between 0 and 1, that means that the numbers in your function the outputs are decreasing, which means that it is a decay. Okay? So with that in mind, let's do some examples. I'm going to write an exponential function and you have to determine whether it's growth or decay. Number 1, f of x equals 2 times 1/4 to the x power. The question is, what is the base here? Well, since the base here is 1/4, this means that it's a decay. Okay? Number 2, f of x equals 7 times 5 to the x. In this one, since the base here is 5, that means we have a growth. Okay? But sometimes these functions are a little bit more sneakier. Not more sneakier, that's not a word. Sneakier. So we have this example. F of x equals 3 times 4 to the negative x power. Alright, so notice that it's not quite in the form a times b to the x. So we have to rewrite it so that it is. Well, looking at one of our exponents, laws of exponents, 4 to the negative x power is the same as 1 over 4 to the x power, which is the same as 1/4 all raised to the x power. Now we can see that the base is 1/4, which means that we have decay. Okay, now let me make this a little smaller so I can squeeze in a couple more examples. 4, f of x equals 0.75 raised to the negative 2x power. Okay, so pause this video, see if you can figure out whether this is growth or decay. Okay, now here's the solution. Well, I can write this as 3/4 raised to the negative 2x power. But then I have a negative exponent. To make it positive, I just take the reciprocal of 3/4, and all of a sudden, now it's positive 2x. Then I'm going to raise this to the second power and then raise the whole thing to the x power, giving me 16/9 to the x power. Well, 16/9 to the x power means that my base is 16/9. which is greater than 1. So what we have here is a growth. Okay? All right, make sure you have all the notes down, because in class we're going to be working on a problem set where you will be doing textbook exercises very similar to the examples you just saw in this video. See you in class!